Hi everybody again, this is Professor Johnston, and I'm here just to kind of illustrate a little bit about the Wiener process that we have been looking at. And this is kind of a chart that we had seen once before, where I was looking at sample paths of a normal random walk, which in the limit becomes that Wiener process. And I was doing it for different time steps. And so I had a very crude time step here of 0.1 all the way down to a time step of 1 over 10,000, right? And this is just from 0 to 1, say, for example. So, and the Wiener process would just be the limit of this as delta t gets really small. And kind of like the purple line, basically. And, these are just sample paths. Each one has its own sample path, so you can see what I'm doing here. This is Matlab online, by the way. It's a great tool. You can do it, I believe, through your Farmingdale account, and you can use it. So you can see what I'm doing here is I set dt, and then I take a bunch of normal random variables where the variance is equal to dt raised to this exponent, which I set at 1/2 up here. So it's the square root of dt. That's the variance, square root of dt. And I multiply a bunch of random normal random variables. And then what I do is I cumulative sum. So I create that random walk. And I get that cumulative sum. And then I plot it, right, as a stair function. And so this is just one. Each one of these has got their own sample paths. So, if I run this again, I'm going to get a different group. I'm going to get a different group over and over. I keep doing it. And what I was saying is that, hey, at any point in time, the reason why we had to have this dt raised to the 1/2 power was twofold. Number one, we wanted the variance per unit time to remain a constant as time went infinitesimally small. That was our first reason. And if you remember, we said, oh, well, if I make that just say dt raised to the 1 power, dt, what happens is my variance per unit time decreases as dt decreases. And if I go to the limit and make dt 0, then the variance per unit time will go to 0. And I'll get a very boring stochastic process that's equal to 0, basically, forever. So we had that. And then we also looked at the other, where if I raise it to too high of a, or too small of a power, 1 over 64, for example, then my variance per unit time is actually increasing as dt decreases, and that's not good either, because then the variance will ultimately go to infinity. So to prevent the variance per unit time going to 0 and infinity, I want it to be a constant. The only choice was 1/2, right? And that gave us these nice graphs. And the other thing, what it does is it says, hey, at any point in time, right, if I was to look at all the samples from this purple, generated from this purple line, and I'm going to do that in a second, and compare it to all the samples generated from this blue line, that when I get to this point here, 1, it's going to look like a normal 0, 1 random variable, whether I took steps of very small steps or whether I took very large steps, right? So the variance per unit time, right, is a constant, but when I multiply it by dt, which I'm doing for each one of these, when I get to the end, I'm going to have the same normal random variable, no matter how I sort of sampled it, right, no matter how I sampled it. So just to kind of show you that, let me go, say, figure 10, go to a different figure over here. And let's say I do a histogram of, I think I called it n samps, and I'm going to use, say, 20 buckets. And this is going to be, not just n samps, comma 1. So I'm going to use, so what I'm doing here is I'm going to show you a histogram of the, all those blue paths. I ran 1,000 runs, okay? I ran 1,000 runs. And so I go back here, I took these blue lines and I did it 1,000 times. And then I just plotted up a histogram of where I ended up at this time 1. Okay? Now it's not going to be perfect because it's only 1,000 runs, but hey, it looks pretty normal 0, 1, right? Kind of distributed, right? Not exact. So let's take a look at the, if I had broken it up into a smaller interval. Same thing. If I had done smaller interval, same thing. And if I had done all the way 4, same thing. So I could have done more runs. I only did 1,000. Took about, I don't know, a few minutes on the computer. Could have done 10,000, 15, 100,000, whatever, and you would have gotten a better approximation. Let me just do one of these things here and let's say hold on. And then plot the other one on top of that and say, yeah, so there they are, right? They look pretty much exactly the same. You know, obviously it's only 1,000 samples, so it's not going to be perfect. But basically, no matter how I slice and dice, time, I'm getting the same normal random variable at time 1. In fact, any time. If I take a slice here, I'm going to get the same normal random variable. Slice here, same normal random variable. And that's why we needed that square root of dt. Now, this is all, this is all the random walk, right? And so what I want to do is just show you what that Gaussian white noise process looks like. So I'm going to go, let's take another figure here. Put it there. And so here you notice I plotted the, and I'm going to go all the way down here to the most discrete, smallest time sample we did. All right, so we had the purple line here, right, the purple line. And so I'm going to plot the increments, the actual difference between adjacent samples here, right, which is kind of like the derivative of this thing, right? In fact, that's how we generated this. That's how we generated that. So I'm going to plot that. Plot, and it's going to be t times, instead of x, we're going to be applying dx. Notice I use the word dx on purpose. And there it is. That's what a Gaussian white noise process kind of looks like. And that's at the same sampling. That's basically derived from this purple curve. So if you take differences in adjacent values here and just plotted that, which is kind of like taking the derivative, right? It would be scaled, obviously. This is what you get. So this is the dx. This is what you see. This is the dx that kind of feeds into, you know, the Brownian motion, right? Where we have mu dt plus sigma dz. This is the dz. This is the dz, which is sort of the random component, right? Random component. So hopefully that's useful. You know, what I'll do is I'll try to come back with another video looking at taking this dz and putting it into, say, different functions and seeing what happens. Well, we could try something right now, right? What if I was to plot up figure 3 and say figure 3? And let's say I want to plot up, instead of x, plot up x squared, t comma x. What does this thing look like? Wow. Interesting. So, I mean, let's just let me just run that again, see what happens. So let me just plot. So you see you have your drift, you see, so first off it's positive, right? And you've got your drift component here, right? Remember you're supposed to have a drift component, right? Because I'm plotting up x squared. That drift component was, I think according to that last video, was like 1/2 n times n minus 1, so it would be basically dt, right? So it should drift up to about, you know, on average 1, you know? So I'll explore this a little bit more in the next video, but I just wanted to kind of give you a little bit of a flavor about this Wiener process once again, right? All right, we'll talk soon.